Good morning, everyone.
Good morning, everyone.
Thank you for joining us
Thank
today
you.
and welcome to Production Modeling Corporation's web presentation. Today's topic is Simulation Supports Operational Decisions, Making Your Operations Adaptable and Nimble. Our presenter today is Edward Williams. He is a Senior Technical Specialist at PMC. Please note that your microphones have been muted to prevent any background noise throughout the presentation, as this presentation is being recorded. If you have any questions, please utilize the Q&A button at the bottom of your screen. We will be holding a live Q&A session at the end of the presentation where your questions will be answered. So please just put those in the Q&A and we will get to those at the end. If you have any issues with sound or visual errors, utilize the Q&A as well, and I'll do my best to help you as the presentation continues. This webinar, as I mentioned, is being recorded, so if you miss anything, don't worry. It'll be uploaded to our YouTube channel at a later date. Now, before we get started, I'd like to do a brief introduction into PMC. Since 1979, PMC has helped over 700 companies by completing more than 7,000 performance-enhancing initiatives worldwide. Our commitment to excellence has brought us to the point we are the largest independent industrial engineering services firm in North America. PMC has worked with hundreds of businesses across all industries to improve. If you want to go back, Ed. Yep, sorry about that. At the bottom of your screen, as you can see, PMC has worked with hundreds of businesses across all industries to improve their performance. But shown here are just a few of our current and repeat customers, if you want to check that out for a little bit. Okay, next slide. Today's session will be focused on simulation, but here's a sampling of the other services that PMC offers. These include laser scanning, drone and photogrammetry, traditional IE services, simulation modeling and analysis, safety and quality, steel detailing and fabrication, and jig and fixture design. Now I'd like to turn things over to Ed to begin our presentation, Simulation Supports Operational Decisions. Ed, take it away.
Thank you, Brian. Ed Williams here, the old gray wrinkled one. I've been working in simulation 43 years now, and I've been at PMC since retiring from Ford, so it was manufacturing usage back there, in 2001. Joined PMC in 2002. Simulation is usually thought of, traditionally, as supporting major decisions, capital expenditures. How should we lay out the new plant or hospital or warehouse? How many machines do we need? How many workers should we hire? How many forklifts are required? And simulation indeed does do a very fine job helping with those decisions. But on a lower key but vitally important note, especially with businesses needing to be so nimble these days when unexpected things like pandemics happen, there's so many day-to-day decisions. What should our staffing levels be day-to-day, week-to-week, even hour-to-hour in case of some of our clients? Scheduling policies. In a warehouse, routing policies. In a delivery company, routing policies for the delivery trucks. In a large hospital, where do we send the patients next when it's medically feasible to do multiple tests and interviews in any order? Maintenance policies. The machine breaks down now. It was scheduled for routine maintenance in a couple days. Should we pull the routine maintenance work forward while we have it taken apart to fix it? Inventory policies. Where is the sweet spot between stockouts and overstock in terms of reorder point and reorder quantity? Those are examples of routine but vitally important day-to-day decisions they very much affect the bottom line, partly because they're made so often. And there's so many objectives. Keep the work going. Avoid excessive, don't have a stock out, but avoid excessive inventory. Keep the background work moving. Like, well, you've got to sell groceries to the customers, but you also have to keep the shelves stocked or you won't be able to sell any groceries to the customers. Short queue lengths. Get the queue line, but lower the administrative costs. Not too many, but then the queue lengths get longer. And we want downtimes to be both rare and short. All those different objectives, and as I sort of dramatized, likely they conflict with each other. So what's a manager to do? Well, think simulation, among many other things, I might add, like value stream mapping, facility layout, work scheduling. I can hardly overemphasize that the more simulation works together with all the other tools of industrial engineering, the more synergy you get, the more value added you get from simulation and its industrial engineering colleague methods, and the plumper your bottom line gets. That's a happy thought. So certainly include simulation in your thinking. And as I mentioned, leading in, simulation should already have guided many of your very fundamental long-term high capital expenditure decisions, such as the ones listed on this slide. These are things that simulation has already given guidance to for many of our clients. And now they come back for the day-to-day decisions, like the ones coming up on upcoming slides in this deck. Now, first of all, if you want a simulation model to be accurate, you need three fundamental foundation pillars. The model has to model the right problem using the right conceptual model, and then that conceptual model has to be written correctly in computer software. There's multiple computer softwares, very good ones for simulation, 10 or 12 of them. I know 5 of them. At PMC, we use about a dozen. All the engineers know at least 3. Second pillar, the data. GIGO, garbage in, garbage out. The input data has to be accurate insofar as possible. It may have to be estimated. And those data have to be analyzed correctly before putting them into the simulation model. And that's where the statistician comes in. If you need one, I'm handy. The experimentation. There may be an initial transient period called warm-up time. When we do basic simulation training in software usage, we cover that extensively. Look all over the potential solution space for solutions that are feasible. Otherwise, you might overlook the best one. And test the sensitivity of the results. If an input parameter, I just mentioned, data may have to be estimated. If the input data is estimated and may be inaccurate, then it's important to understand if that data were to change a little bit, would the key performance metrics of your system change a little or a lot. That's what sensitivity refers to. The higher the sensitivity, the more carefully the pertinent input data need to be collected or estimated and analyzed. And when comparing many alternatives, maybe dozens, we often have that, it's necessary to use an appropriate experimental design. And that's where detailed knowledge of DOE, the statistical nickname for design of experiments, comes in. The output of a simulation model often should and often does go right into a heavy-duty statistics package for complete interpretation, guiding management to the correct decisions. And I've given an article here as a reference from the Winter Simulation Conference. That's an annual conference every December. I keep up to date on simulation developments. So for examples of some of these day-to-day, week-to-week decisions, what should the reorder policy be? The two fundamental numbers are, when you reorder, how much should you reorder? And how low should your current stock get at the time you reorder? And making an accurate decision requires consideration of all these questions. What is the rate and variability of material usage? Is there a quantity discount? How bad is a stockout? Is it bad, horrible, or catastrophic? Our clients usually characterize it as one of the three. And how long before you place the order and you receive it? And is that time variable? If you overstock, are your goods going to spoil? Say when we work with grocery store chains, are they going to get out of style or out of date? Are they vulnerable to theft or shrinkage? And how much is it costing us to keep that capital tied up in inventory? And how much does it cost to place an order? Just the paperwork. And simulation can then guide those decisions. And here's an example of that point, one of the studies we've done. The hospital contained its own pharmacy that certainly did not want to run out of drugs. The patients didn't come in to get the drugs. The nurses had to come to the pharmacy, get them, and hand carry them to the patient's bedside. And running out of a drug would be toward the catastrophic end of the scale. And input data to this simulation study we did on behalf of a hospital included the bullet point shown here. The stockout cost was enormous, as illustrated in the third bullet point. So by season, simulation determined what the reorder point should be and how much you should reorder. And those were the benefits. Bad things went down. Both stockouts and administrative costs, we'd like to get them down. Now, here's another example. In fact, I already alluded to the first one. The machine goes down shortly before routine maintenance would be undertaken anyway. Should the routine maintenance be pulled forward? Well, very likely, yes. You have the back of the machine taken off already to get at the insides. the mechanic's already there. Well, provided that the person doing the routine maintenance is also qualified to do the needed repair, which may be more complex. That was an operational issue one of our clients told us about because they were the subject matter expert on these matters. So we had to know to ask those questions. Can the maintenance and the actual repair be done in parallel? Can they share resources? And how much is that machine costing you for every hour it's not running? How much work is piling up right in front of it? And simulation specified how long X and Y should be before the maintenance should be pulled forward. And here's the example for this presentation. This was in a warehouse that was our client. After too many of the ceiling lights in an aisle go out, it's too dark in there to be safe, let alone see what you're picking. Wasn't so long ago, I ordered an air purifier and got a bird bath. That company had a little bit of trouble with picking. And replacing those lights, oh, they're way up in the ceiling, get the ladders out. It's high worker expense. You can't pick anything out of that aisle while the workers are up on the ladders. And a revision to this policy was, if a lot of the lights are burned out and you're on the verge of replacing them, well, there's some that are still on, but they're likely to burn out soon. That's an interesting probability theory question. How soon? Should we replace them now or squeeze the last bit of life out of them and then replace them later, bringing the workers back, the ladders back, and so forth? And the policy in this particular warehouse involved the forklifts very similarly. The forklift needs maintenance. There's still some life in the battery, but not too much. Should we replace the battery a little early, even though it isn't dead as a doornail yet? And simulation gave guidance to the client, and the battery costs did go up because you weren't milking the last bit of life out of the batteries before they wearily groaned their very last groan. But the benefits outweighed that increased battery cost, as shown here. There was a good improvement in the forklift availability time, and the net gain, balancing the two, was 7% to the bottom line. Now, this was in a hospital. Medically, you don't dare do this without first asking the doctor. Can the tests be done in either order? Sometimes no, and then you put this, you don't go into this. But very often the answer is yes. Then, well, which order is more efficient? How long is the line at each laboratory and the lab schedules today? Current and projected workload. How many appointments are pending to come into this lab for this particular test? And how long does each test take? And a simulation model running in the background on the office computer, this model we built runs day after day on a real-time basis. And the healthcare worker, the nurse or the aide, ask the software, should I tell the patient go to this lab for test X or this other lab for test Y, and then come back and go to test X? day-to-day, hour-to-hour guidance. And that type of work, we did that at a large clinic, and we got good improvements after we gave the simulation model patient arrival data. Percent of patients needing each test times and resources. The wait times went down at some of the labs by almost 5%. There was a corresponding increase at other labs, but that was held to less than 1%. And like most clinics, this client, on their surveys, they used a 7-point Likert scale for patient satisfaction, and the improvement was about half a step, certainly significant. When should the backup line be open or closed? You've likely seen this at the grocery store. A dozen cash registers, long lines at 1 or 2, the other 10 are closed. The lines are getting longer and longer. You've got a worker you can bring to the register, but that worker is restocking the shelves or working in the back, and that work's important too. So when do you tell the worker the line is over a certain length, leave the restocking work for now, come up, open the register, get the line length down, and then when we get the line length down, go back to the restocking inventory work you were doing in the back. Well, these various data points come up. What orders should be given to the backup worker? And a subtle but important point is, how efficient is the backup worker, for example, who works mostly in the back and doesn't work that many hours on the register? Is the backup worker 10%, let us say, less efficient than the experienced cashier in ringing customers through? So the simulation can tell the grocery store manager, when the line gets up to a certain length, open the backup, call a worker there. When you get the line back down to Y, shorter length, close the backup register for now and send the worker back to the ongoing tasks. And that's what we did on behalf of one of our grocery store clients to set policy. The backup worker was about 10% less efficient, needed 10% more time per customer. Under various conditions, such as day of the week, hour of the day, the simulation determined the best values of X and Y per the previous slide. And customer satisfaction went up. And we watched, well, the obvious queuing metric is average time in queue. But I commend to people in service industries, there may be a threshold, 5 minutes, 10 minutes. There's characteristically a tipping point at which people rapidly start to get angry. And what is the percent of customers who have to wait longer than that tipping point? And here the manager felt it was 5 minutes based on long industry experience and talking with customers. Oh, if I have to wait more than 5 minutes between 2 pairs of numbers on my wristwatch dial, that's when I really start to get annoyed. And the percent of customers who had that too long a wait went down even by 8%. Very good improvement. And similarly, scheduling lunch hours. This often applies in service industries. When I renewed my driver's license, I wish the Secretary of State office would use these ideas. Well, lunch is often the big rush time. The same time your workers would like to eat lunch, or like noon, that's the time people rush in because they're on their lunch hour from their own work. How rapidly does it build up from 11 o'clock on to 1 in the afternoon? Are the customers arriving in the late morning more or less impatient than the customers arriving about 1 p.m., maybe after they've eaten lunch? And is there a situation, if there's already a moderately bad backup from 11 o'clock, does the noon rush become just impossible? And simulation can guide a decision like this one. Tell a certain number of the workers to eat lunch at 11. The others eat lunch at 1 o'clock. And no, you cannot eat lunch at noon. That's a common one, even without simulation. And that was the case in the restaurant, where the rush was at lunch. So the workers had to eat their own meal before or after the customer lunch rush. So we worked with the restaurant to gather data on arrival and party sizes, 1, 2, 3, 4 people. How many people who made reservations characteristically didn't show up? The manager was expert in, if we have a certain number of tables, how many servers do we need active? And it improved worker morale because the workers were asked their lunchtime preference. And the simulation produced those wait times. And the implementation helped the restaurant reduce the number of diners saying, well, I already waited in your lobby too long, I'll go somewhere else. And morale of the workers did go up. That was measured on a Likert scale, because most of the workers' preferences, not all of them, it's like saying, well, everybody wants to take time off at Christmas. Not everybody can. But a greater percentage of the workers could have their preferences accommodated, and that improved morale on the average. So there's a few of many scenarios where we've worked with clients. Notice, please, the wide difference in industries: healthcare, restaurants, grocery, warehousing, and so on. And I'll turn this back to our nice host, Brian, for Q&A.
Yep, thank you, Ed. So now we'll enter into the Q&A section of the presentation. If you joined a little late, be sure to utilize the Q&A feature at the bottom of your screen if you want to ask Ed a question. But Ed, we did have a few questions come in, so we'll get started with those. But please, if you have any questions, type those in the Q&A and we'll have Ed address those for you. So Ed, the first question we had come in: how are the relative merits of alternatives modeled in a simulation study best compared?
First, you ask the client, as we always do, even before turning the computer on, what performance metrics are most important to you? The important performance metrics might be throughput. That always comes up in a factory. In a service industry, the performance metrics might be average time in queue, average number in queue, maximum time in queue, sort of what's the angriest somebody got. Number of stockouts below a certain number, what's that number? So we then run a simulation model under the scenarios of data we've collected. The simulation software will tell us what those KPIs, key performance indicators, will be, and specifically whether they'll be within the parameters above, below, set by the client. And we can also build statistically, here's where statistics comes in, we can build confidence intervals for those performance metrics. For example, we can say the probability is 10% that a party of 5 in the restaurant lobby will have to wait more than 10 minutes. The probability is only 4% that a party of 2 in the restaurant lobby will have to wait more than 5 minutes for a table. And those probability thresholds guide managers in choosing among alternatives, because we do that for each plausible alternative that the client asked us to model to see which alternative was to be preferred.
All right, thank you, Ed. Another question, it's a little long, so bear with me. I can see putting different numbers like number of machines or cycle speed into a model to compare, but how could you put different schedules or routes into a model to compare them without building different models?
Perhaps surprisingly, and as the question suggests, it's pretty easy for a client, presumably unfamiliar with simulation software, to realize, oh, if I were to buy a more expensive machine, I'm considering that has a cycle time of 8 minutes instead of 10 minutes. Somebody goes to the computer and replaces 10 with 8 and runs the model over again. So certainly, and that traditionally has been very possible. More recently, with the improvements in simulation software in the last 10 years, we can, using the right simulation software, and there's several right ones, put 2 different schedules or 2 different routing patterns in the warehouse into the model and tell the computer, run this model twice, first with one schedule, then with the other schedule, but it's only one model with 2 different alternatives inside it. Run the model twice, get the key performance indicators for both alternatives, or maybe all 8 or 10 alternatives for that matter, and print them out and print bar charts and statistical comparisons side by side by side for all the key performance metrics. So that would still be only one model with multiple alternatives inside it.
All right, thank you, Ed. I don't see any questions coming in, so with that, I'll close the Q&A. For a schedule of upcoming topics regarding PMC, please visit our website at www.pmcorp.com. From there, click on the Resources tab and scroll down to Webinars and Events and register for other webinars that may be of interest to you and your team. As I mentioned before, this is being recorded, so please be sure to visit our YouTube channel in the next couple of days. That's PMC Videos, videos with an S, to check out this recording of this presentation if you want to check it out, or this presentation, review the slides, or check out other topics that might find it and pique your interest. I recommend you do that. But with that, that will conclude today's webinar. I'd like to thank everyone for your participation.
Email questions are welcome.
Yep, of course. you think of any additional questions, like Ed said, if you'd like to discuss how we can help you design your own simulation projects that you might need, please contact us at one of the addresses on your screen. And with that, we look forward to working with you or perhaps joining you in another one of PMC's productivity improvement web seminars. Thank you and have a great day, everybody.